right. Good afternoon, everyone. Hope everyone is having an amazing day. It's Thursday, it's the 19th. We're in Atlanta, it's the heat of summer, and yeah, just enjoying staying cool. Today's topic is going to be deep learning with PyTorch. Deep learning, I'm sure you guys all know, has many uses out in the real world, and we're really just scratching the surface. What I kind of want to do today is give you kind of a quick introduction to deep learning. What is deep learning exactly? Um, I know myself, when I was first trying to learn deep learning, it was like, what's all these weights and all these things going around and layers and so on and so forth. So what I really want to do here today is kind of talk about deep learning in a very high level, in a very general sense. And then I'm going to try to introduce PyTorch and why PyTorch is such a great tool to execute deep learning. And finally, what I want to show you guys is a pre-trained model using PyTorch. And again, this whole workshop, it's intended for beginners. I think this is such a cool space, and certainly I'm not an expert, but I want to definitely share, what I have learned in terms of deep learning, how we can use it, and what the capabilities are. And so this whole workshop is really focused on a beginner's perspective. So just keep that in mind as we're kind of going through it. I've kind of set up this lecture such that, yeah, I'm going to be talking about it, but I also want to have interaction from the class. I will try to look at the screen here to see your guys' comments. And definitely, if you guys have questions as we're going through any of this material. So let me give you a bit about my teaching style here. Actually, before I even get into that, I should probably follow my own my own notebook here and first give my introduction. So, of course, my name is Haroon. I am a senior consultant at Deloitte. I've been working at Deloitte for about a few years now. A lot of the clients that I engage in are in the healthcare industries and technology industries. A lot of what I do is SQL data related, running lots of queries around hospital data and giving our healthcare clients all kinds of insights into how their patients looking like in terms of, what kind of payers are coming in, what sicknesses are they coming in for, diagnoses, all that kind of healthcare information, and even now we're shifting a little bit to physician analytics, and we're keeping track of how physicians are taking care of their patients, where they're ranking, and how they're contributing to the overall hospital structure. So yeah, other engagements I've done. Let's see, I've done a K-means clustering for a bank client. That was a really cool project, actually. That was a project where it was a small bank, and they wanted to get a feel of where their customers lie in terms of credit rating. This was a very specialized bank. They did lots of loans to farms. And so it was a little bit of a different system, but it was very much intuitive and very cool project, actually. We got to see, what are some of the high risk categories that farms might engage in, farm businesses might engage in, and what kind of, how that affects their rating. Aside from my full-time gig at Deloitte, I teach here part-time at Georgia Tech, part of the Data Science and Visualization Bootcamp. I've been a part of that program for about a couple of years now. It's a really great program if you're wanting to switch careers. Say you're doing something else and you didn't really like it. This is a great segue into this kind of arena. We teach students Python from A to Z. All the way from the basics, get them comfortable. We start working with APIs, and we work in a lot of cool different libraries too, like SQL Alchemy, Flask. We do some SQL. And finally, we get to machine learning at the end. So yeah, that's a little bit about me, and hope that kind of gives you an idea of where I'm coming from. So now I think we can kind of get into the real meat here. So again, high level, the agenda for today, I want to talk a little bit about deep learning. Okay, PyTorch as a tool for deep learning, running it, and finally, I'm going to show you a pre-trained model using PyTorch. I believe I put ResNet together. So it's going to be a cool project. I can't wait to get there. So anyway, back to what I was saying. So, the kind of lectures I like to have, again, are more interactive. I can't really see a list of y'all. Maybe I can, and I just don't know how. I see people. Oh, okay. I see people. Okay, so I might just do this. I might start calling on random people, but again, it's not to put you guys on the spot because I see there's about 700 of you, so there's no way I can get to all of you. But I do like to kind of call on people at random, and feel free to speak up, shout out if you have questions. I will be monitoring the chat, and so feel free to chime in as we're going along. Does anyone have any questions? Okay, I'll take silence as golden. So, what is deep learning? So, before we kind of even talk about, deep learning itself, let's take a step back and see where it fits in the whole paradigm, right? So, deep learning is actually a subset of machine learning, which is then a subset of AI. So, in machine learning, right, we have lots of different algorithms, lots of different techniques, right? We have supervised, unsupervised, and all the different algorithms that go in there. And of course, that is a part of the broader AI arena industry. And so deep learning is technically its own type of algorithm, its own type of technique. Sometimes there can be a lot of confusion. Is deep learning the same thing as machine learning? Well, yes, it's a subset. Is all machine learning a type of deep learning? Nope, not really. It just depends on what we're looking at. So yeah, again, just a very high level overview of what we're dealing with. So the key difference of deep learning and other machine learning algorithms is deep learning uses multiple user configured layers with neutrons, okay? And the other thing that I'd like to point out here is machine learning so this machine learning, right, the different algorithms in machine learning in general, they require a lot of human intervention. So what do I mean by that? And I want to take a look, I want to point to this little diagram here. So in the past, and I'm looking at this piece on the right, in the past, it used to be that, okay, we have a machine learning algorithm, we have a bunch of data, and some kind of expert would have to go in and do something called feature engineering, okay? And so what does that mean? It means that, someone had to go in and actually create features for the computer to recognize. So let's take a step back here. Let's say we're taking a look at a picture of a human, right? And what does a human have, right? Eyes, mouth, nose, all that good stuff. What feature engineering means in that context is someone would have had to go in and define this is a nose. Look at the edges on the pixels. If I'm pointing to my nose, look at the edges here. Look at the tip. Look at all the ridges. And if you see something like that, that's a nose. And you need to start labeling that as a nose. And then same thing for eyes, ears, mouth, so on and so forth. And so you can kind of get a feel of how, I don't know if tedious is the right word, but very complex, how complex that would be, right? If you had to go in and sit and say, all right, here's all the features that I want you to pull from a human face. Well, there's a lot of features, right? There's skin color, there's tone, GitHub link. Sorry, I'm just seeing your guys' message. Thank you for reminding me, Matt. I will post this this notebook as a link to everyone with all the code. And if I can even share it in an email list with y'all, I would probably do that as well. That's definitely something I can follow up with Amelia on. Ali, I think you had a question, data annotation. Do you mind, feel free to come off mute and tell me what are you thinking there? Nope, a little shy. Okay, that's all right. Feel free to chime in what you mean by data annotation. So you can imagine that this whole process would be pretty tough, right? Again, someone has to go in, identify eyes, ears, mouth, so on and so forth. What deep learning does is takes this whole human aspect out the equation. And I think that can't be understated enough. Like, that's huge. So I saw someone come off mute. Hey.
Hello.
Hey, what question can I help answer? Yeah.
Yeah. So feature engineering is basically, is it sort of data annotation? I mean, You assign or classify a bunch of data.
Sorry, Ali, what do you mean by data? What do you mean by data annotation? Can you be a little bit more specific?
Take, for instance, a picture.
Yep.
I mean, if you're looking, if I'm looking into the camera, maybe my glasses, I can annotate my glasses
Yep.
by pixels. Yeah. So feature engineering is basically the same, right?
Exactly. It's so look at it from the perspective of the computer is like absolutely dumb. It doesn't know anything, and we have to codify that. Hey, Ali is wearing glasses, and this is what a glasses looks like. And you might see a reflection. I'm looking at your picture. I see the reflection. So I might see a reflection. I see the corners, and I see a different color here. So exactly that. It's us telling the machine, hey, if you see something that looks like this could be glasses, and just take a note of that. Does that sort of make sense, Ali? What I mean by
Yeah,
that?
it makes sense. Yeah.
Yeah. Yeah. So again, the whole cool thing about deep learning, right, is let's take a look at the left here. We don't actually need to do this whole step here, this handcrafted features. We don't need to do that. The machine in this case is smart enough to know that, okay, hey, I see like ridges here, and I see this is where your brow is, and I don't know technically what that is, but I recognize it. And if I see that again, I'll know that that's some kind of unique or distinct identifier. And that's really how that's really the big thing about deep learning. It can automatically figure those out. So again, deep learning is a technique for a computer to automatically find representations in raw data. I want to take a quick pause here. Any questions? Okay. Hopefully I haven't lost all of y'all. If I have, feel free to push back. So now that we kind of understand what deep learning entails, let's see if we can kind of peel back the layers a bit. Layers, pun intended. Let's see if we can peel back the layers a bit and see what neural network looks like, right? And so I came up with this like silly example. Hope you guys will appreciate it. I call it the simplest neural network you've ever seen. So I'm a big Atlanta Hawks fan. I live in Atlanta, of course. Let's try to predict how many wins the Atlanta Hawks will have next season based on the average number of fans in their arena. Okay, so maybe more fans equals more wins. I don't know. And I think everyone is familiar kind of with this setup here. And if you're not, feel free to chime in. Here I've kind of annotated some of the code here, and this is the actual code. So here I've created kind of like a simple list of like the number of fans, right? So 10,000, 12,000, 13, 15. And here I just created like a random weight, right? And in this instance, I just put it as, it looks like it's 4 10,000s. Okay. So what do I mean by weight? Okay. Weight in this instance refers to the sensitivity of our model. And so let's run this, and I think maybe we'll have a clear understanding of what I mean here. So here I'm just defining a simple function. Here's my neural network. It takes in some fans, a number, right? And it takes in a weight. And the prediction is based on the fans multiplied by the weight. Okay, so let's see this in action. So I'm going to run our neural net here, right? So I've taken the number of fans in the first, as the 0th item here, and I just multiplied it by 0.0004. And what do I get? A 0.4 probability or percentage value, whatever you want to call it. Okay. So in this example, right, in this very simplified example, I've taken one input, I've taken one weight, and I've received one output. Okay. And I know this is like a very simple example, and obviously the fans, maybe depending on how you feel, maybe the fans don't have an effect on the players, right? They're not the ones shooting the basketball. But anyway, the point of this is kind of the key architecture, the key piece of neural networks everywhere. You're going to see some kind of input. You're going to see a weight attached to that input. And then finally, that weight is going to drive your output. I want to repeat that one more time. So in this very simple neural network example, we have one input, right? The number of fans. We have some very random, I just picked a completely at random weight as 0.0004. And then we have an output. And the output or prediction is based on the multiplication of those two. I want to take a pause here real quick. Is everyone with me? And feel free to push back if I can clarify. Okay. So at its core, this is what a neural network is all about. Now, where it gets complex is when we have multiple inputs, right? So in the real world, it's not nearly as one-to-one like that, right? It's going to be multiple inputs. It's going to be multiple weights, right? And so let's see if we can kind of flesh out our example a little bit better. Okay, so now I said, okay, let's create a version 2 of our neural network, right? So let's have a few more inputs. So we have fans, as we did before, and then let's have something like win-loss percentage, and let's have something like players who score 20 points per game or more. Okay, so now we have multiple weights, right? Because we would want multiple weight. We would want one weight for each input. Okay. So here, what I've done, I've modified this example slightly. And again, feel free to push back if I can clarify further. So here I have the weights, okay? And I have them kind of sequentially set up. So this is the weight, same as before for my fans. This is the weight for my win-loss percentage. And this is my weight for players above 20 points per game, okay? So when we have multiple inputs like this, what do we want to do? We want to do something called a weighted sum, right? Because if we want a complete picture of all of our prediction, right, whether the Hawks are going to win or not, we want to somehow combine all these inputs and weights into one big sum, right? And so here, just right below that, I defined like a quick weighted sum function. And I want to actually take a pause here. Here, I've kind of defined it out, but when you work with the libraries that do this, you're not going to have to do any of this. This is pretty much done implicitly. The only reason I'm kind of showing you this is to kind of peel back the math behind it, because personal anecdote here, when I was trying to first learn this, I definitely got scared off a little bit in terms of, whoa, this looks like some complicated math. And then finally, once I started digging and reading into it, I thought, oh, okay, it's actually, I'm not the brightest bulb, so it's even something like I could understand, right? And so this is kind of how the method that really helped me understand, like, oh, okay, there's a bunch of inputs and there's a bunch of weights, and this is how the flow goes for a neural network. Any questions so far? Again, feel free to come off mute, and it's not just me yapping up here, guys. It's also you guys. So feel free to come off mute and ask questions, and yeah. Okay, so now that we have now we've defined our weighted sum, right? So again, the weighted sum, we're going to do something like, okay, we're going to multiply this weight with this fan, and this weight with this win-loss percentage, and this weight with this player's points per game. So there's only one, okay? And we're going to combine them together, and then we're going to make a better prediction. So we went from, looks like we went from what, 0.4 to 0.40, so a little bit better, which is odd because the number of fans, anyway. So the point here is, what this whole process that we just did, it's a weighted sum, right? And it's a dot product. Now, you may have heard this in a slightly different word, right? Matrix, vector multiplication, whatever you want to call it. To me, this is kind of the way that made a lot of sense and was more straightforward. I didn't have to think about the horrors of math. So, if this helps you see it, hopefully it does. But for me, it definitely helped me see it a lot clearer in terms of, hey, at its core, what is a neural network? right? And so it's in this example, in a very, very simplified example, it's a weighted sum between two vectors. We're multiplying straight through the weights and the values in each list. So again, these were the list of the weights that I had. I put them down here for reference. I don't know why it shows it as scientific notation. It's kind of annoying, but anyway. The point that I'm trying to drive home here is this math, this type of math where we're looking at two different lists in this case, and we're multiplying them through, this math is 100% the same in concept to much more difficult problems. Here, I'm showing you vectors, right? But this could very easily be a matrix, right? And it's nothing to do with the red pill or blue pill, but what a matrix is something like this, right? So we have rows. I forgot to annotate this, but this also helps me see it very clearly. We have something like rows and columns. And then after matrix, we can have 3 dimensions. We can have 4 dimensions. We can have as many dimensions as we want. Of course, the complexity gets infinitely larger, but the basic idea is still going to be the same, where we're taking a weight and we're multiplying it with our inputs. Now, how those weights and inputs are structured, that is going to be dependent, right? That's going to be dependent on your data, what it is you're trying to learn, use deep learning for. That's going to be a separate issue. But the math here is going to remain the same. And so I want to kind of spend a minute here talking about this, right? Just kind of drive home the point where in this very simple example here, right? It looks like we just have a one input to a multiple output, right? So here is your input, right, in this side on the left, and here's your output on the right. And so let's see, I want to pick on someone. Scott, I just see your name, Scott Hadzik. If you don't mind, and if you're not comfortable coming off mute, that's totally fine. How many weights would you say that each output multiplies to? How about that? How many weights does each output is each output responsible for? Okay, maybe Scott's unavailable. Edgar. Yeah, exactly. The number of inputs. I saw you. Yep. So here, this output is driven by the weights of 3 different inputs, right? So again, let's see if we can kind of link it back to our example with the Hawks, right? So here would be our different inputs, right, on the left. So we had a number of fans, we had win-loss percentage, and number of players score above 20 points. And each of those has a unique weight that combines to an output. Yep. Does that sort of make sense, what I'm trying to get at? I know in this example, in the Hawks example, it was a very simple 1-to-1 and a many-to-1. But in the real world, it could be, so this is the real world, guys, right? So you have your input here, and then it gets transformed, and then it serves as the input to this layer. And you can see all these different connections, right? And so when I first saw something like this, like I was just kind of afraid, like, what am I looking at? Is this a fractal? Maybe, I don't know. But really what this points to is, hey, each output can be determined by multiple weights. And at its core, that is exactly what's happening in deep learning. Deep learning, the computer is trying to find, this is, I use, that's a good one. At its core, deep learning is always trying to find the combination of weights that gets you to that place that you need to go, that gets you to the closest prediction, that gets you to the closest estimate of your prediction. So all these weights that are happening here, they're constantly getting tuned, fine-tuned, updated. There's different techniques. I will talk a little bit about those different techniques later. But again, the key here is that I want you to take away all neural networks are is this combination of what we saw above. Let's go back to our simple example. It's an input, and it's an input, it's a weight, and it's an output. Now, those parameters are going to change. You'll have multiple inputs probably, and multiple weights, of course, and the output will probably be just still the same output, but at its core, that is what's happening behind the scenes. I want to take a pause here. What questions do we have? Again, guys, feel free to come off mute. Don't be shy. Go for it. Okay. I'll take silence as golden. So, is the decision on weights more art than science? So, it's not art. Maybe it could be art. Trial and error. Yes, absolutely trial and error. Absolutely that. I'm going to talk a little bit about how that trial and error, how one way you could think about that trial and error, but at its core, John, you're absolutely right, where the computer is eventually going to find that combination of weights that leads to the highest value. Or sorry, I should rephrase that. That leads to the lowest error. I'm sorry, let me rephrase that. The computer is always trying to do this trial and error that is trying to find the error as close to zero as possible, okay? And so I think we've heard, I think if you're a little bit familiar with machine learning, right, we've kind of come across this phrase here, predict, compare, and learn. There could be other iterations to this. Is it possible to start with weights that result in unstable? Yes, yes. So at the very beginning, so great question, William. At the very beginning, very similar to how I had up here, right, where I basically just had a random weight. That's exactly what the computer does. It doesn't know until, you know, it throws something at the wall, and does it stick? Yes, no, and from there, it goes and does its magic. Yeah. So at the very beginning, at that very first step, it is going to pick something random, like a random weight, because at that point it really doesn't know, you know, how close or how far it is. And once it starts iterating through that process, it picks up on, okay, I need to go in this direction, I need to adjust my learning rate like this, and so on and so forth. Then how do we choose it? It's completely random. You can start with a completely random weight, and from there, the machine will automatically pick up and adjust as it goes along. Great questions. Here, so Sunil, here, what I did, again, I just chose a very arbitrarily oh, I just realized this thing is probably in the way. I don't know if you guys could see that. This is a completely arbitrary number that I picked. There was no rhyme or reason to it. I apologize if that was in the way. My apologies. I just noticed that too. Okay. Okay. So here, Matt, I have a delay, so can't speak. The essential flow is giving the computer. We have the outputs, and it generates the weights to yes. From there, we can use new inputs to see yes. And so here is where you have, so in this example, right, in my Hawks example, I had a very basic one-to-one, right? I had one input and one output. But in the real world, Matt, like I think what I'm envisioning you're asking is, yes, in the real world, you'll have multiple layers. And so let's kind of break this down maybe. Here's going to be your input layer, and then here's going to be your first output layer. But then this layer acts as an input to the next layer, and then to the next layer, and so on and so on. So pretty much it's like this whole, you know, this whole process of going back and forth. And I'm going to try to get into that like a little bit. Again, I don't want to get too much into the weeds here, because I know I tailor this as much as a beginner's perspective. But I think you're right, Matt, in the sense that here, this is an output for this layer, but then here, this is going to be the input for the next layer. And it's only until this process completes at the very end, with all these weights happening, that we get to this final output. Okay, So the next thing, so hopefully I've given you guys kind of like a decent overview of how neural networks work in general. And so the other part of our neural network, right? Well, how do we know if it's any good, right? Okay, we're making these predictions. I think Sunil had a great question. We just choose a weight at random. So how do we know? How do we know if this prediction is worth anything? Maybe it's worthless. Yep. And that is a great question. And so I kind of set this example up a little bit such that I want to kind of show the flow of how the computer compares its result to what the expected result should be, and then how it learns. In other words, how it picks up on, hey, I'm too big or I'm too small. I need to tune my weights like this in this direction, and then let me see if I can get a little bit closer. Okay. So here, I've kind of made some, again, just some arbitrary assignments here. I have a weight of 0.5, I have an input of 0.5, and my goal here, I want to get to 0.8, okay? So let's go ahead and run this cell. So again, very simple. My prediction following from our example earlier, right? We're just multiplying it through. So my prediction is 0.25, but my goal is actually 0.8, right? And so one of the ways that we can measure error is something called mean squared error, okay? And what the mean squared error represents is how much of an error we have in our prediction. And so from our prediction. And so you might be wondering, okay, Haroon, why are we squaring this error, right? So the example that I like to give is, let's stick with the basketball example. You know, if I shoot at like a 35-degree angle, right? And, you know, I miss the hoop, let's just pretend I missed the hoop by 2 feet, right? You know, is it 2 feet up? Is it 2 feet down? What direction am I getting? What direction do I need to, what direction am I off from the goal, right? And so what squaring allows us to do is get rid of that negative value. That's going to be important when we're talking about comparing like errors. Sorry, when we're comparing like outputs. One of the things that can derail an algorithm here is if you include those negatives, you might get a distorted view of what the actual error is. So hang on, since you set a goal, that makes it supervised learning. In a sense, I would say that, but this is more an unsupervised learning. Again, the computer, and I think when I show this example at the very end, I do have an example set up where we will do a PyTorch neural network. Is it knows what it's looking at. So I wouldn't say it's supervised, but I would say that the computer is smart to know what, for example, a dog looks like. And in the example I'm going to show you, what I think it's like a Labrador Retriever, what a Labrador Retriever looks like. Okay, so going back to this example, right? So again, we're squaring the errors, right? Simply because we want to get rid of the direction of our error. If we have a direction in our error, that can cause some little distortion. You know, if we have negative values and positive values, and we try to average those guys out, we could easily end up in the situation where they cancel themselves out, okay? There are many other ways to measure error. Just for this lecture, I decided to just talk about mean squared error because I think it's widely used. Certainly, it's very widely used, and I think conceptually, it's a little bit easier to see why we want to choose it. So if your criticism is, you know, hey, the squares make big errors bigger and small errors smaller, I would agree with that. And there is going to be a way to handle that as we go along. Okay. So I think this question popped up earlier, right? So are we just picking random weights? And the answer was yes. So let's try to look at it in terms of a knob, right? And the audio knob, or maybe like the temperature knob, I guess. So what I like to describe it as the hot and cold method, right? So we adjust the weights up or down to reduce the error. right? Like a radio knob. I should probably change it to AC knob. And the goal here is to set the error, is to get to the error at 0 as close as we can. You know, in the real world, we probably don't get to 0, but as close as we can. So let's run the same example that we did up here, the same exact one, and let's see what happens when we increase the weight, right? So what I want to point your attention to here is this line. So I defined another variable. I set it LR for learning rate, and I just set it equal to 0.1, okay? And here, I've added our learning rate to our weight, okay? So I'll go ahead and run this, and let's kind of see what we get here. So it looks like the weight got us a little bit closer, just a little bit. So our prediction was 0.3, our goal, and it looks like our mean standard error was 0.25. And here, it was 0.30. So what does this tell me? This tells me that, yep, it looks like we're in the right direction. Seems like we need to increase, the weight. As we increase the weight, we can get closer to our prediction. What is the learning rate? Yep. So Hannah, what I want you to take away from this is think of the learning rate as like a step. You know, we're taking a step. So if you're on a mountain, right, and you need to go down, right, you can take big steps to go down, or you can take little steps to go down. And sometimes you need to go up to go down. I don't know if you've ever done mountain hiking, but sometimes you have to go up and then down and up and down. And really, what I want you to take away from the learning rate is it's something that we add. It's just something we add to the weight, to our original weight, to see if we get closer or not to our goal. Does that make sense, Hannah? So here, when we increase the learning rate, ergo, we increase the weight, we get closer to our goal. Now, if we decrease the weight, it looks like, so very clearly we can see that, oh, we're going in the opposite direction. This is like a very, very, very simple way to kind of get a feel of like, hey, this is how the computer is going to think about this. It's going to try to add a little bit, then subtract a little bit, just to get that weight right. And then finally, it's going to say, oh, I'm getting hotter and colder. But as you can probably tell, it's pretty inefficient, right? You'd have to probably do this like a whole bunch of times to finally get in the right direction. And the other point that I want to make here is it gives us the correct direction to go, but it doesn't necessarily give us the correct amount. We could overshoot our goal if we only stick to, I think both examples I put 0.1 here, sorry. If we stick to this 0.1, it's very possible that we can overshoot our goal. How do we choose learning rate? If we choose inappropriate learning rate, we can skip local minimum. Yep, I'm gonna try to answer that, Sunil. It's coming. But great question. Love the enthusiasm, guys. Keep the questions coming. Okay, so one of the ways that we can kind of figure out, hey, are we moving in the correct direction and are we going by the correct amount, is by something called gradient descent. Now, I know that sounds kind of scary. And again, my goal in preparing this presentation was to take out as much math as possible, because math is like the scariest four-letter word for me. I don't know about you guys, but math, yeah, it scares me. Okay, so let's see if I can try to help you understand what gradient descent is, okay? So I kind of took the same from the last example, same weight, same goal, and same input, but I tweaked it a little bit, okay? So we're going to iterate through this example 20 times, right? So here in this for loop, we're going to iterate 20 times, and we're going to see how close we can get to our prediction, okay? So again, our prediction is the input multiplied by the weight. Here is what I want to pull your attention. Sorry, not here. That's the mean squared error, but it's coming. So here's the mean squared error, right? Here's the new code that I want to introduce. So to get the correct direction that we want to go to, we can set up a formula something like this, where we subtract our goal from our prediction. So we're basically taking this part and we're multiplying it by the input. I want to repeat that. So to get the correct direction and the amount, we want to subtract our goal from our prediction, right? So this part right here. And then we can multiply that by our input. I think when I run this cell, hopefully it'll be a little bit more intuitive. So let's take a look at the results that we get, right? So let's kind of walk through these, a couple of these iterations, see what happens. So in our first iteration, so it looks like our direction is 0.275, our updated weight. So again, here, sorry, I didn't talk about this line. I'm sorry. So with this new direction and amount, we can update our weight here to reflect this new learning. This is where the learning is really happening in this line, these two lines right here. This is where the real learning is happening. Because once we plug in this new direction and amount into our weight, again, think about it in terms of the learning rate that we talked above. This is basically our new learning rate. And it's not necessarily like an arbitrary amount that I just picked, right? Like 0.1. It's actually driven by the error here and by our input itself. And so that becomes our new weight. Is everyone kind of following me here? Feel free to speak up, guys, if I can clarify. Okay. And I know we only have about 12 minutes, but I think we can get through it. So here in our first iteration, right, we have an amount here. So this is our very first, right, this prediction minus our goal. And then our new updated weight based on that is going to be 0.775. Now, here's where our error is, right? The same as we saw before. And here's our prediction. But look what's happening iteratively, okay? Do you see what's happening here? Our error is slowly but surely getting smaller and smaller. And I did this 20 times. It's very much arbitrarily. I don't know why I picked 20, but I think I know why, because I got closer and closer. But let's take a look at this. With just this simple formula right here, what's happening? My error is decreasing, and my prediction, I'm getting better. I'm getting better. So we started at 0.25, and again, our prediction, we're trying to get, our goal is 0.8. Okay, so here our prediction 0.385. Sorry, 3875, 0.49, 0.56. Is everyone kind of getting the feel of this? Like, yes, this is a very simplified example, but when you run a deep learning with all those different layers under the hood, this is the same thing, same exact thing that's happening. It's iteratively learning, it's updating itself, it's getting a new weight, it's applying that new weight. Hey, am I getting closer? Okay, it looks like I am. Keep going. Does everyone kind of get the sense of this? And so when I did this 20 times, I think at some point, yeah, it was just, I probably have to do this like another 10 times, I get to 0.8. But you can see that, hey, after all these adjustments, I can get pretty close, pretty darn close to my goal of 0.8 there. I want to take a pause here. What questions do y'all have? Don't be shy, guys. And fret not if you're like furiously writing this down. Fret not. Again, I'll link up with Amelia and make sure that you all have this. If I have to just email it myself, that's totally fine. I'll try to put this somewhere where you guys can access it. Yep. Typical for the rate of increase toward the prediction goal slows with each. Yep. So as we get closer and closer, right? In this example, it seems like, yep, I guess the law of diminishing returns, we're getting closer and closer. So yeah, I agree with that, John. Maybe, maybe for more nuance, maybe we just stop here. Maybe, I don't know. It's very much a judgment call. With neural networks, of course, in real neural networks, how about that? It's going to be a lot different, but the mechanics are still going to be the same. It's going to try to iteratively get better and better and learn, and finally get us as close as it can to our prediction, to our goal, predicted goal. Mm-hmm. So in the interest of time, I'm going to kind of glance over this a little bit because I definitely want to get to where I show you, hey, how we can use a pre-trained model. But just know that this kind of iteration, right? It does a few things here. So when we're multiplying our pure error by the input, let me go back upstairs. When we're multiplying our pure error by our input, few things are happening here. We're able to stop, right? So if the input is 0, we can automatically protect ourselves by also having the direction and amount of 0. We can take note of those negative reversals, right? So in the instance that our weight is positive, but our input is negative, we can control for that, and vice versa. That's another big thing here. We could have weights that are negative, or we could have inputs that are negative, and we need to be able to control that. And what this allows us to do is take that into consideration. And finally, scaling. If we have a big input, we should expect that the weight update should also be big. Because if we're multiplying this input and it's big, well, I would expect this number to also get bigger as well. So all this is to say that in graphical form, this is what you're going to end up with. And I apologize, it's a little too big. Let me see if I can zoom out just a little bit. Yeah, let's go like this. All of this is to say that in graphical form, this is what it looks like, okay? So on my x-axis, I have the weight, and on my y, I have the error, right? So what happened in this instance? My error was really high at the top, right? So let's look at it graphically. My error was probably somewhere here, and then my weight was, you know, wherever it was. It was like, you know, let's see, what was the weight here? We started at 0.775, and then it progressively got bigger. Can everyone see that, right? It gets to almost 1.5. So it's maybe somewhere here. It's kind of approximating a little bit. And so what this is doing is saying, hey, as you get closer and closer, that slope, you should expect that slope to be smaller and smaller and smaller. And that's exactly what we saw here. Is everyone understanding kind of this picture and the relationship that I'm trying to paint just in a different way? Again, our error is decreasing along this whole line. And when we get to pretty much like at where it's 0, that is the weight, that is probably going to be the optimal weight for our neural network. And I don't really want to get, if I can save myself, I did talk a little bit about derivatives, but I think maybe we can skip that because I know we only have 5 minutes and I want to make sure I get to the rest of this. I want to take a quick pause here. What questions do we have? Again, this will be available for y'all. I'm more than happy to share that, and I'll make sure to get that to you. So I want to get into, we have about five minutes maybe. I know we started a little bit late, so maybe we can go just a little bit. Amelia, feel free to interject. I do want to kind of run through an example of a pre-trained model, okay? And I did have this really cool site here. You guys can take a look at it on your own. I messed around with it. I had a lot of fun, actually. So what's so special about PyTorch, right? So, typical stuff. It's very easy to work in. Documentation is amazing. Take a look at this link. Go to the documentation. It's very, very nice to read. And I don't say that a lot because I don't like reading. Anyway, it's very good to read. And here is a typical project flow of a deep learning model, right? So here we have all of our data sources and we're doing pre-processing. I'm going to talk a little bit about this in a minute or so, but what I really want you to take away here is, here's our data source. And this processing, again, think about it in terms of the Hawks example that we had, right? We did a little bit processing, like very, very minimal, right? And we had to multiply the weights by the inputs. But think of that on a much larger scale here, because that's exactly what's happening. And so all that is being happening. And then finally, we're doing our training, right? And so here you have all these computers that are doing, thousands upon thousands of calculations. What we have the benefit of is other people much smarter than us, they've done the training for us. And so all we need to do is call that trained model. You know, what's that saying? We stand on the shoulder of giants, right? So I can change the light bulb. But in this case, run pre-trained networks. So people have done this training already, and all we need to do is start from here, the trained model, and we can go ahead and start messing around and having fun with this. So I have an example here that I want to walk through. So again, really quickly, instead of the very basic vectors that we did in our example, PyTorch handles data with something called tensors, right? But the idea is still the same, guys. It's 2D tensors, 3D tensors, 4D, so on and so forth. It's the same concept, just called a little bit differently. Okay, so the pre-trained network that I want to show you guys is ResNet. I will include some links about ResNet here after this is over. Rest assured, it's a very popular pre-trained network, and it's very good. It's a very good one. And so here, I don't know why that came, but anyway. So here, let's kind of go through it, this example. So I'm importing a bunch of stuff. Again, what's happening here is not necessarily that relevant. I'll get to the relevant, I'll make sure to highlight the relevant parts. Here, so within PyTorch, there's something called Torch Vision that allows us to import popular data sets and models, okay? And here's like a very simple list of all the models that are available in Torch Vision. So you have AlexNet, DenseNet, GoogleNet, so on and so forth. If you see a number here, like DenseNet 121, the 121 you can think of as a DenseNet network with 121 layers. So if you see a number like this, just know that typically that means the number of layers it has. And so for our purpose, we're just going to import the AlexNet, okay? And you know, I just kind of want to show you this just for the sake of showing it, but really, this is what it looks like graphically. It's what I think is much easier to see. So there's a few layers here. It starts in 96 and goes 256, 386. So here's all of our multiple layers, right? AlexNet is a pretty simple neural network. It's been used and it's a very good neural network. Here, though, we're going to do something a little bit different, a little bit more complicated. We're going to walk through ResNet. So let's go ahead and import that. So, and again, all of this text here, it's really not relevant in terms of what's happening. All I really want to say here is these are all the different layers, pretty much very similar to this, but ResNet 101, as you can tell, has 101 layers. So the graphical representation for this would be pretty big. So again, these are all of our layers here, right? And so what I want to do is show you guys like a really cool example of, hey, let's just grab like a random picture of a dog somewhere, and let's see if this pre-trained network can pick up on, is it a dog? And specifically, what kind of dog? So this is going to be the flow here. So I went ahead and found like a random image of a dog. I'm going to display it later. We're going to resize it, and we're going to do a bunch of data pre-processing here. And then finally, we're going to punch it into our pre-trained network. And then we're going to find, hey, which label corresponded with the highest score, with the max score here, okay? And then finally, we have like a basic, it's like a simple text file. This is how, so real quick background on this, ResNet is based on ImageNet, which is a collection of images. I think it's by Stanford University. It's not important, but what is important is matching it up to this list, okay? So let's run this. So here, again, this is where the pre-processing is happening, right? So it looks like it's doing some resizing, center crop to tensor. Here, what I would say, if you guys have heard the term boilerplate, it's more of a boilerplate type code for this example. We just need to know that to process an image into ResNet, we just need to resize it, okay? So here, I'm using something called the PIL. It's a library that helps us import image. And I found this random image of a dog. I'm going to display it in a second. So here's a picture of the dog I found. I think I don't even remember what website I found it. But anyway, it's a golden retriever. It looks like. I'm not a dog person. But anyway, the point is, found a random dog on the internet. And here, we're going to pass in that image into our pre-processing function that we defined right here. So we're passing in this image into our pre-processing function. So we've done that bit. And so now this next line of code, this unsqueeze, what it does is it returns a new tensor with a dimension of size 1. So again, I don't want to get too much in the nitty-gritty. Just think about the example of how we just multiplied vectors earlier, and it's the same kind of analogy that's happening here. Now, here's where the fun's going to happen. So here, it's going to evaluate. So this model, it's an evaluation mode, and we're going to evaluate this image. Okay. So again, a whole bunch of other stuff. We don't need to necessarily consider it for now. But what we do want to consider is now that we pass in our image, what do we get out? Okay. And so here is our final output, right? In this format, you would probably say, Haroon, what is all this gobbledygook? And I would agree, right? I would totally agree. But we can match this output to what's in our predictions. And so here is where I open, again, it's like a very simple text file that has like all the labels of it. And we're basically importing it here, okay? Here, we're getting the max value from our output. So we're getting the max from our output here, okay? And so here, what we want to do then is basically take that max value and convert it as a percentage. I don't want to get too much into the weeds of what's happening here, but really what I want to point out to you guys is when you run this code, we get this. So it looks like the computer is suggesting with an 89.4% accuracy, hey, I think this is a Labrador Retriever. Again, I'm not too much of a dog person, so let's just make sure it looks kind of like a, I mean, maybe. If someone's a dog person, feel free to chime in. It's just way off, but it certainly does look very similar. I thought it was a golden retriever, but what do I know? Here is the max value that it found and the corresponding label that it found. And I did this just as like just to round out this exercise. Let's just get a top 5 here real quick. What are the other things it found? So yeah, so I guess I don't know my dog breeds. It did say with 7.6 accuracy, it's golden retriever. Show it a possum. That's a good one, William. Yep. If we had time, definitely I would do that. Definitely. What is interesting though is on the images that this model is trained on. Notice something interesting here. It's saying, oh, there's a very small chance that I totally messed this up, and I think it's a tennis ball, which is kind of funny because I guess dogs are always catching tennis balls. So maybe it saw a bunch of images with dogs and tennis balls. So that is kind of funny. And then greater Swiss mountain dog, I suppose, but can't comment too much on that. Yeah. So again, the real world implication of this, and let's take a step back here. How many lines of code did we really need, right? Not a lot. You can today, right now, import AlexNet, and again, I found like a very random image of a dog. I just Googled it. I said, okay, let's just find an image. I didn't even know how close it would be, how close of a value I would get. I really didn't know. I just found it and I said, okay, let's see how good it is because I want to know myself. But again, the beauty in this is a lot of this work has been done for you in the sense that you don't need to have these complicated setups where you're training a model for hours upon hours. People have done this for you. And really, like that list of models that I had up here, you can import any one of these today and do exactly what I did and say, hey, tell me what you think of this picture. Is it a dog? Is it a cat? So on and so forth. This is really the beauty of deep learning here. One of the other topics I did want to get into, but I realize we're out of time, is something called generative adversarial networks, or GANs. This is another very, very popular, very cool thing about deep learning where you have something called a discriminator and a generator. So I'm sure you guys have all heard about deep fakes, right? Pictures of Obama and he's giving speeches and so on and so forth. So what a GAN, generative adversarial network, does is basically parse out those reals and those fakes. And with cycle GANs, so taking it to the next step, with a CycleGAN, it's able to actually make those deep fakes and deep fake images and deep fake videos. It's a really cool thing. If I had a little bit more time, I would have probably got into that. But again, I did want to keep this very high level and just try to demystify, all the things that you may have heard about on deep learning. Maybe you've heard like it's scary or this and that and the other. I hope today's lecture, workshop, whatever you want to call it, kind of demystified some of that. And I hope I was able to give you some context around, hey, this is what deep learning is all about. And this is how easy it is that I can have, like, let's see, one, really not that much lines of code, I think. And all of this was boilerplate type code. You could easily look this up on the PyTorch website and get this information. It's not a mystery. Here, again, this is part of the transformation process, the pre-processing. But once you have this and you have the image of the dog, it's running a few other lines and getting an output. William, show to possibly, yeah, does PyTorch only work? No. So here, I specifically wanted to show a pre-trained network because I don't have a, super powerful computer, and B, I don't think we all want to stare at me training a model for hours upon hours. We don't have time for that. You can build any custom model that you want using PyTorch. You can build, you can go into the real nuts and bolts, William, and figure out, hey, I want to build this from the ground up, from scratch, and I want to have this many layers and this many neutrons. You can customize all of that if you like. Here, I just wanted to demonstrate, very quickly how something like, again, this is something off the shelf. This is something that, you just go to the website, look at it a little bit, and you can start plugging this into your own application right away. Yeah. I apologize if I went a little bit fast towards the end. I wanted to make sure I got to the end. I know we started just a little bit late. We had some technical issues. I appreciate everyone's patience throughout this lecture. I want to thank each and every one of you for attending. I greatly appreciate it. Before I kind of let you guys go, this is one thing I like to do in class as well, is I like to do two things. I like to do something called DW, and I like to do something called DD. So no, I'm not the designated driver, and no, I'm not DW from Arthur. But anyway, because that's the response I've got. DW, what does DW stand for? DW stands for did well. So, whatever you guys thought I did well on, hey, were my explanations good? Did I explain it very clearly? Did I answer your questions? Did I have good jokes? My jokes were okay today. Go ahead and feel free to shout out what you think I did well. And then definitely, as take the good and the bad, right? I can take the medicine as well. So in the DD, do differently. If I could do something differently, what would you suggest as like a feedback, right? This is my first time doing this kind of topic, so full disclosure, I was just slightly nervous, but I think it went pretty smoothly, and I'm glad you guys stuck around and you guys didn't boo me off stage. So, but definitely, if there's something you guys are interested in, I would definitely like to hone in on this, and maybe you can go more in detail, more in depth on some of these examples, and as time permits. And of course, if Amelia will have me back, I don't know. So anyway, if you guys could do two things in the chat, DW, did well, and DD, do differently, I would really appreciate that. It really helps me improve, guys, and I can take this forward, definitely apply it to the next time, and of course, get better. DW, how can I connect you back? Yeah, let's do this. So I can pull this up real quick. I'll just really quickly put this in the, where am I going? Oops, what did I do? What did I do? Fair enough, William. I saw that. Fair enough. Haroon, can you move to chat? How do I do that? I'm sorry, I'm really dumb. How do I move to chat? Just so we can end. Like that? Oh, I'm sorry. Yep, you're right. So how do I stop this? Close video? Okay.